All right, so you've got a software architecture exam coming up. You're in exactly the right place. In this explainer, we are going to break down all the essential concepts you absolutely need to know to nail that test. Let's get right into it. So, here's our game plan. We're going to start with a pretty intense story that shows why architecture can literally be a matter of life and death. Then, we'll get into what it actually is, look at some common patterns you'll see everywhere, dive into the core principles of good design, and finish up with why writing it all down is so critical.
You know, instead of starting with some dry, academic definition, we're going to begin with a story. A story that proves without a doubt that architecture isn't just some abstract thing in a textbook. It can have absolutely devastating, real-world consequences.
This quote right here is the whole reason we're starting this way. It comes from the tragic case of the Therac 25. This was a computer-controlled radiation therapy machine back in the 80s, and its story is just a foundational and honestly a very sobering lesson for anyone in software. So what happened? The Therac 25 gave patients catastrophic overdoses of radiation, and it all came down to a fundamental flaw in its design. See, the software was basically copied and pasted from older machines that had physical safety locks, actual hardware to prevent accidents. But in this new design, they took those physical safeguards out and decided to rely completely on the software. So when the software failed, and it did, it failed silently. No warnings, just tragedy. Digging into the why, you see these classic architectural failures. You had type coupling, which is a huge no-no. It meant the user interface and the actual radiation gun were all tangled up in the same memory. A bug in the UI could literally affect the radiation beam. Then you had race conditions, a timing bug where if an operator entered data too quickly, the system would get completely confused. And maybe the worst part, zero fault isolation. A single error could just ripple through the entire system and bring the whole thing down. It was, no exaggeration, a perfect storm of bad architecture. Okay, so now that we've seen the devastating consequences of getting architecture wrong, let's back up and properly define what it actually is so we know how to avoid these kinds of disasters. A really important idea to get your head around is that architecture isn't just one giant single diagram. It's more like a collection of different maps of the same city. The person planning the electrical grid needs one map, but the person planning the postal routes needs a completely different one. Each map, or view, hides all the details that aren't important for that specific job, making a complex system so much easier to understand. So, for your exam, burn this definition into your brain. Architecture is the big picture. It's about breaking a system down into its main pieces, the components, and then defining the rules of how they're allowed to talk to each other. It's the fundamental blueprint you create before anyone writes a single line of code. And it's so important to know the difference between architecture and low-level design. Architecture asks the big, hairy questions, right? How is this thing going to scale to 1 million users? What are the major subsystems? Design, on the other hand, is about the nitty-gritty details. What happens when I click this button? What's the best algorithm to use right here? Think of it this way. Architecture is the city plan. Design is the blueprint for one single house in that city. Okay, now that we know what architecture is, let's check out the common tools an architect gets to use. These are called architectural patterns, and they're kind of like the standard plays in a football team's playbook. So what's a pattern? Well, it's basically a proven recipe for a common problem. You don't have to reinvent the wheel every single time you build something. These patterns give us all a shared language and a solid jumping-off point for tackling design challenges, whether you're building a website or a system for a spaceship. First up, the layered pattern. This one's a classic. You organize the system into a stack, kind of like a layer cake. At the very top, you have the presentation layer. That's the user interface. In the middle, you've got the business logic, which is the brains of the operation. And at the bottom, the data layer, talking to the database. Now, the golden rule here is that a layer can only talk to the layer directly above or below it. This creates this fantastic separation of concerns. It means you can completely swap out your database without having to touch your UI at all. It makes everything so much easier to maintain. Next, we've got pipes and filters. The best way to think about this is like an assembly line. Data comes in one end, it goes through a series of stations. Those are the filters, and each station does one specific job to it before passing it down the conveyor belt, the pipe, to the next one. This is perfect for systems that do step-by-step processing, like a compiler turning your source code into a program. The client-server pattern is one you use every single day. Your web browser is a client asking a web server for a page.
Your banking app on your phone is a client talking to the bank servers. The server is the central authority. It holds all the data and the logic. This is great for keeping everything managed and secure in one place. Now, for a more modern approach, microservices. Instead of building one giant monolithic application, you build a bunch of small, independent services that all talk to each other. Netflix is the poster child for this, right? There's one service just for user logins, another just for recommendations, a different one for actually streaming the video. Since they're all independent, the recommendations team can push updates 10 times a day without ever affecting the team that handles billing. This architecture is built for speed and massive scale.
So, underneath all these different patterns are two principles that are so fundamental, you absolutely have to know them for your exam. They're called cohesion and coupling. Let's break them down.
First up is cohesion. This is all about how focused a single piece of your system is. Does everything inside that one component serve a single clear purpose? Your goal always is high cohesion. Think of it like a perfectly organized toolbox. All the screwdrivers are in one drawer, all the wrenches in another, everything belongs together.
So, for instance, a module with high cohesion called user authentication would only handle logging in, logging out, and resetting passwords. A module with low cohesion would be a jumbled mess that handles authentication and calculates shipping costs and formats reports. You want high cohesion because it makes your code understandable, reusable, and way easier to fix when something breaks.
The second principle is coupling, and this is about how dependent different components are on each other. If you make it change to one component, how many other components are you going to have to change to? Now, with coupling, your goal is the exact opposite of cohesion. You want loose coupling. You want your components to be independent, not tangled up like a plate of spaghetti.
And this brings us right back to our story about the Therac 25. That system suffered from incredibly tight coupling. A change in the user interface could actually break the hardware control. In a loosely coupled system, the UI and the hardware would be completely separate, talking to each other through a stable, well-defined interface. That way, you could redesign the entire UI without ever having to worry about it accidentally causing a lethal error.
All right, we're almost there. Let's talk about the final, crucial piece of this puzzle. A truly brilliant architecture is totally useless if it only exists in one person's head, and that is where documentation comes in. Look, documentation isn't just busy work you do at the end. It is the blueprint. It's what guides the entire team. It's how you make sure important things like security and performance are actually built in from the start. It's the map that future developers will use to maintain and evolve the system long after you're gone. It's the single source of truth for everyone. And you need to remember this quote because it's 100% true. If you don't intentionally design and document your architecture, one will just happen. An accidental architecture. And those are almost always messy, fragile, and dangerous. Conscious, well-documented design is what separates successful systems from failures. And that's really the key takeaway here. Architecture isn't something you just do once at the beginning of a project and then forget about. It's a living, breathing blueprint that has to be taken care of, adapted, and evolved as the system grows and the world changes around it. Keep that in mind and you'll be in great shape. Good luck with your exams.